Hello and welcome everyone to the week 5 live session on the course Experimental Biochemistry. I am Srijan Sen from IIT Kharagpur and today I will be taking your live session. So let us start with our lecture slides and then we will be discussing with the assignments. Okay, so I'm sharing my slides with you all. Yeah, good evening everyone. Good evening. So I guess my slides are visible to you all. Yeah, that's good then. So let us start. Okay. So today's lecture will mostly cover the chromatographic techniques that you had all studied actually. So we will be discussing, so I guess you have gone through the lectures that were shared with you or whatever you have seen on the week 5. Okay. So I will be discussing more or less in brief because we cannot cover each and every portion. I will be talking about the most important sections or the important portions that are important when we are talking about chromatographic techniques. So a very brief introduction about the protein structure, which we already talked about it before, is that all proteins are mainly composed of amino acids which are linked together into a peptide chain via the formation of a peptide bond or multiple peptide bonds, and each peptide bond occurs via the removal of one molecule of water. And there are 20 amino acids which form the building blocks of proteins, the naturally occurring amino acids that determines the different properties of a protein, or the properties of the amino acids determine the structure of a protein. Now proteins are composed of one or more peptide chains that folds into a three-dimensional structure, including several linkages with non-protein molecules, like it can interact with lipids, carbohydrates, even proteins or small molecules. Now the combination of number and type of amino acids and non-protein components of the tertiary structure also determines the function of a particular protein. From here, I am going to introduce you to what chromatography is. So the basic goal of biochemistry, when so the concept of chromatography first came when we tried to understand what biochemistry actually deals with. So one of the major goal of biochemistry is to separate and identify the chemical compounds. It's one of the most effective techniques for accomplishing the separation and identification of a particular molecule. Right now, if you have to separate it from a mixture, these chromatographic techniques play a very important role. So when we talk of chromatography, there are two very important terms that we need to keep in mind, and that is basically your mobile phase and the stationary phase. And the molecular species separate because they differ in the distribution of these two phases, right? So there are many types of chromatographies. I have mentioned only a few over here, but the major ones being your adsorption chromatography, the partition chromatography, ion exchange. You have the gel filtration chromatography, thin layer gas chromatography, affinity chromatography. So these all of these chromatographic techniques need not be used for the separation of one particular mixture. Rather, you need to find out or need to understand which chromatographic technique you want to use that will specially be able to separate out only your desired product, okay, or desired molecule. So so the typical reasons why we need to purify a protein, or the major aim of purification is to first is to identify the function of a protein. Why is it so? Like for example, if it's an enzyme, you would definitely not want to have a a mixture or a contamination of other molecules that try to interfere with the activity of an enzyme. For that, we need to isolate the protein or the particular enzyme in its pure form. So purity is a major issue for understanding the actual function of a particular protein. Secondly, comes the structure of a protein, because in the presence of other molecules or contaminants, the protein might not be able to fold properly. So its native function as well as structure is hampered over here. That is why purification needs to be done. Thirdly, to use the enzyme to generate the desired product, it's somewhat related to the function. And if we want to produce a commercial product such as a diagnostic or a therapeutic, uh, you definitely want the medicine or the therapeutic to be very much pure. Like everything is not like 100% pure, but it has to achieve a certain level of purity to become any sort of a diagnostic or a therapeutic. Now, there are a few key steps in this purification process. One, when no two purifications are the same and the separation is faced with a variety of techniques, you can use anyone to achieve the goal. So, the release of the target protein from the starting material, followed by the removal of the solids, then you have to remove the water, contaminants, and you have to stabilize the target protein. Okay, so this is not very much important. Let's first start with the few of the chromatographic techniques that we use for the separation of mainly proteins. Okay, so the first one, it's a very interesting technique, the size exclusion chromatography, also known as the gel filtration or the gel permeation chromatography. So it generally uses, we use this ACC or a size exclusion chromatography to separate biological molecules and determine the molecular weights and the molecular weight distribution of the higher molecule structures or the polymers. So we use it to separate larger molecules or macromolecular complexes from smaller proteins, or a polymer-like structure, a multimer, oligomer from a monomeric structure. So separation of molecules according to its molecular weight, or you can also tell about the molecular weight distribution. Now, when an aqueous solution is used to transport the sample through the column, we call this as the gel filtration. When the organic solvent is a mobile phase, we call it gel permeation chromatography. So it's the same, it falls under the category of size exclusion chromatography. Depending on the type of mobile phase that we are using, we give it different names. So the separation of molecules, we call it as the fractionation, and the size of the pores in the beads determine the exclusion limit. Like what is the exclusion limit, what goes through the beads and what goes around the beads. Why is it important? For the resolution. Like for example, if the column has a capacity to only separate molecules having a size of 10 kilodaltons to 200 kilodaltons, if a protein is of a very higher size, like you have a protein molecule of 400 kilodaltons, it will not be able to separate it out. It goes into the void volume. That is what we know of, that is what we can call it as what goes around the bits. So it goes around the bits, it goes into the void volume, so it cannot separate a higher molecular weight protein. What can it separate? It can separate only those proteins that have a that falls within the particular limit. So what is the limit? Say for example 10 kilodaltons to 200 kilodaltons. So the exclusion limit for that particular column is 200 kilodaltons, above which it cannot separate it out. Great. Now if we want to separate a protein of even higher sizes, we need to use a column that has a higher exclusion limit. So the principle behind this is that we have a mixture of molecules that is dissolved in a particular solvent, that's a mobile phase, and it is poured into the chromatographic column, which is a formation of different microscopic spheres, which we call as the column beads or the stationary phase. Now the mass of the beads within the column is referred to as the column bed. Now these beds, what it does, it acts as traps or sieves and functions to filter the small molecules which get trapped into these pores. Now these beads are basically not of one particular size, so you have different sizes for different proteins, and the number of more variety of sizes of beads this column bed is comprised of, you have the higher is the resolution, because the protein molecules can enter through these beads and the resolution power basically increases. So what is resolution? If you are all know, resolution is the property by which you can separate out two peaks of very small sizes fantastically, right? So what happens over here is that the larger molecules passes around or are excluded from the beads. So if you have a variety, if you have a bigger bead over there, the molecule enters. If it's even bigger than that, then it just passes on and it's excluded from the beads. Henceforth it goes into the void volume. Okay, and then we have the larger sample molecules that cannot or can only partially penetrate the pores, whereas small molecules can access most of all the pores. So larger molecules elute first, smaller molecules elutes later, right? So this is the property. So when you are run a protein or a mixture of proteins through a chromatographic column, you need to make sure that the higher molecules or the higher molecular weight proteins elutes faster, because it has to traverse a very shorter path, because there are only a few number of bigger beads. But for a smaller molecule, it has to enter all the beads. You have to feel like that. It's a small molecule, it has to enter all the beads, it cannot exclude the path. Henceforth, it takes a longer time, hence it elutes later. So see, so this is just a schematic where we can see the size exclusion chromatography. Here is a mixture of different molecules or proteins, and you have the beads over here. So the small molecules are entering over here, whereas the big molecules just excludes the path. And you see there are different sizes. So for bigger molecules you have this, for smaller molecules it enters, whereas the even bigger molecules it does not enter and it goes over, it passes the particular bead, right? And then what happens, so the small molecules have to enter each of these paths and then it has to come. So the smaller molecules enter many pores in the gel, and hence it travels very slowly, and after which you have the medium sized and the large molecules that did not cover all the beads, and it elutes faster, the smaller molecules eluting at the last. Now, so we need to calculate the column volume as well. So the total column volume is the summation of the volume that is occupied by the packing of the column plus the volume of the solvent in the pores plus the free solvent volume. So it's a summation of all the three, Vg, Vi and Vo. Now, the different components of the size exclusion chromatography includes stationary phase, the mobile phase, you have the columns, pump and the detectors. So the stationary phase is the semi-permeable porous bead with a well-defined range of pore sizes. Now these beads are comprised of your cross-linked polymers. Now the degree of cross-linking is totally controlled such that you have different size of the pores, or the column bed is made of a variety of pores for a better resolution and for a longer resolution of a higher molecular weight proteins. Smaller pore sizes are used for rapid desalting of proteins or for protein purification, whereas the intermediate pores are used to separate relatively small proteins. Sorry, are you saying anything? Hello, all good? Great. Now, very large pore sizes are used for purification of biological complexes. The stationary phase used for gel exclusion chromatography includes your dextran polyacrylamide and the dextran polyacrylamide mixture, which we call as the cefacryl column. Now each of this is available in variety of ranges of pore sizes in the beds to permit the different macromolecular separation of different sizes, and there is a vast range. So if someone is using it in their lab, it depends on what type of mixtures they want to separate, what are the different types or the sizes of proteins they want to separate out, and they use a different type of column. Now, a good stationary phase characteristics are very important because because it should not be affecting the protein that you are, or a molecule that you are trying to separate it out. That is why it should be chemically inert. It should be inexpensive, though I'm not very sure how inexpensive these columns are. It should not react. That's very important. It should not be reactive with the component that has to be separated. It should not even react with the eluent. It should be colorless, uniform in size and shape, and it should be mechanically stable, irrespective of the type of mobile phase that we are using. Now, from where I ended, the mobile phase. Now, the mobile phase is basically the liquid that is used to dissolve the molecules that we call as the buffer. It is also the mixture of biomolecules that is dissolved in the buffer, which we call as the sample that we load onto the column. The choice of mobile phase is used in any separation that will depend on the type of separation to be achieved and the component that needs to be separated. So the most common eluents for different polymers includes your chloroform. These are organic like chloroform, tetrahydrofuran, dimethyl formaldehyde. Okay, so you have the material like the synthetic elastomers and what type of solvent you use over here. You have the polyolefins. Okay, you have the trichlorobenzene, dimethyl formamide. You have proteins, and for polyacrylamides you use special water or buffers. Right. Okay. So this is the entire system of size exclusion chromatography, where you have the buffer that passes from here. Here you have the injection valve from where you inject the protein sample or a mixture of proteins, and then it passes on to the through the column, and it gets onto the detector. So the detector you have, and the mobile phase is constantly in use. You have the detector, it detects over here, and then the pumps are being managed from over here. You can control the flow rate and all, and then it enters into the, after being detected, it goes on to the data station or the yeah, you say why colorless? It's because, for example, if you have a colored protein, it's very important because you cannot be able to track a protein. Now, it's not always very important to have a colorless column bed, but for example, if you have colored proteins, now all proteins are not colorless in nature, but if you have a colored protein, you can also track it from where you can actually track that your protein is traveling through the bed. That is why having it colored, or even if the beds are colored and you want to use some kind of a mixture that actually reacts with the particular color, because when you're making these beds and you're adding a color, it often happens that the color or the chemical interacts or reacts with a particular protein. That is why it is recommended not to have color. At the same time, it also adds to an advantage that if your protein is colored in nature, you can actually track the your protein moving through the column, and it looks very beautiful. Now, so we have the pumps over here. So these pumps maintain a constant flow rate that has to be maintained during the entire chromatogram, because from here you have to actually resolve your protein. So a constant flow rate has to be maintained. It's not like you, yeah, first you run it at 1 ml per minute and then at 0.5 ml per minute, because then what it will do is it will actually disturb your x-axis. So your x-axis is either the volume or the time. It is in the x-axis we track the volume or time, and in the y-axis we have the absorbent. So if you are changing the flow rate from time to time, it actually hampers the mobility of your particular mixture of proteins or even your protein, because sometimes it's moving fast, it does not know when it has to move slow. So it somewhat affects the protein traveling through the particular column, as well as it will hamper or it will cause an error even in the detection when you are detecting in or analyzing your graph. So a change in flow rate by only 0.1% can cause an error in a molar mass up to 10, and most pumps can only reproduce the flow rate to 0.2 to 0.3%. Now we also use inline filters in the solvent reservoir to prevent any particles, or we also say not to allow the entry of any air bubbles and all from coming into the pump heads. Then it might damage the valves and the pump seals, because then the pump stops, because usually this ACC is a very sensitive instruments, and even a small air bubble or a particle can actually interfere with not only your experiment, rather it also damages the beads. So we use syringe pumps or the reciprocating pumps. Then we have the detectors. So there are many types of detectors. You can check through them, like the bulk property detectors, solute property detectors, ELSD. You have the molar mass sensitive detectors, which you might be mostly using the LALS detector, light scattering detectors, and the MALS detector. Okay. So the application of this technique is protein fractionation, then purification, molecular weight determination, separation techniques, and also understanding the quaternary structure, because higher molecular weight proteins elutes later. And we also use it for desalting, buffer exchange, copolymerization studies, and so many other applications are there. So these techniques of using one technique can do several other things as well. Now, so I guess size exclusion chromatography is clear to you all. Why copolymerization? Because, for example, if you want to study a protein-protein interaction, right? If you want to study a protein-protein interaction and the two proteins interact very well in a good affinity range, then what will happen? You do the experiment with the single proteins, like you have protein A and protein B. So first you do the experiment with protein A and protein B, and then you add the two proteins outside, definitely, and then you inject it. So what will happen? You will see a very vast shift that is equal to the total of the two proteins. Okay, so the molecular weight will be close to the it will elute at a much lower volume or elution volume range. That means it shows that the two proteins interact very well. This can happen even if your protein has the tendency of oligomerization, then the same thing happens, right? Okay. Moving on to the next type of chromatography, which is affinity chromatography, right? So affinity chromatography, from the name we can understand some kinds of, we are talking about some kind of interaction or an affinity type. So these techniques offer higher selectivity, hence high resolution and high capacity for the proteins of interest. So purification that would otherwise be time consuming, difficult, or even impossible can be done with an affinity chromatography, because not all molecules have an affinity for a particular substance. But if your protein of interest does, it's very easily usable to, or recommended to use such an affinity chromatography. There are so many affinity types that we know about, which we can actually use in our system, or which we can incorporate in our protein of interest for having an affinity towards that particular substance, and hence we can be able to purify it. So these techniques can be used to separate active biomolecules from denatured or functionally different forms, to isolate pure substances at low concentration in large volumes, to remove any kind of specific contaminants. So you inject a mixture of proteins over here. You have a bead over here that is tagged with a particular substance. Your protein binds with this particular bead. So adsorption of the object materials happens over here. The other impurities or the contaminants are removed via the washing, and then you use another substance that has a better affinity for this particular substance, and that basically is involved in eluting out your proteins. Okay, so what happens over here, it's not only affinity chromatography, but also at the same time it undergoes competitive binding, okay, during the time of elution. So your protein has an affinity for this particular bead, or you can say this particular ion. Then it gets absorbed, then you wash out the contaminants and then you elute. During elution you have to use a substance that has a better or higher affinity for this particular bead or ion, and then it binds, competitive binding, and your protein simply elutes out, right? Somewhat it looks like this. We have better ways as well. So right, so affinity chromatography separates proteins on the basis of reversible interaction between a protein and a specific ligand that is coupled to the chromatographic matrix. So the kinds of elution can be your pH elution, ionic strength elution, competitive elution, chemotropic elements, reduce polarity to the event. So you can elute it in many ways. Okay, but not most of them are recommended for proteins, because the moment, for like for example for a pH elution, you cannot simply change the pH, because that can also interfere with your protein, and when you're eluting out your protein, it can entirely damage your protein. Same goes for ionic strength, because suddenly if you want to increase the ionic strength or reduce the ionic strength, it also damages the protein molecules. And then reduce polarity can be possible. We use competitive elution, like I said, you have a molecule, you want to use a molecule that undergoes competitive binding. Usually we do not use any chemotropic agents, because these are chemical molecule. Yeah, I'm coming. Why is it different from ion exchange? When I will be talking about ion exchange, you can actually get it. Otherwise, I'm telling you. We usually do not use chemotropic eluents, because what I want to talk over here is about basically focus on the proteins. So you would not want to treat this your protein of interest with any chemicals or denaturing agents and all, that will actually open up your protein or hamper the function of a particular protein. So how is it different from ion exchange chromatography? If this is an so in ion exchange chromatography, basically what happens first is that so you have a negatively charged protein that binds to the positively charged column, or vice versa, you have a negatively charged column that binds to a positively charged protein. But it's very different, because here the affinity is not based on charge. Here you have a particular tag, or the protein itself has an ability to um, what can you say? The protein has an ability to bind with a particular ligand or a particular substance. Okay, here the charge is not involved. That is why it's affinity chromatography. It's the internal property of the protein that we want to utilize for the binding. Okay. Also, the charge is also an internal property, but here the column is uncharged. Okay, can be charged, because if you're using some kinds of ion, it can be charged, but we do not want to use the charge-charge interaction over here, right? Next. So for the elution, the simplest case is that we change the buffer composition that elutes. We change the buffer composition that elutes the bound substance without harming either the protein or the ligand. Then extremes of pH or higher concentration of chemotropic agents are required for elution, but they can cause permanent or temporary damage to your protein of interest. And the third and the fourth one, what it does, it's that specific elution by addition of substance that competes for binding. So these methods can enhance the specificity of the media that use group specific ligands that I was just mentioning. So, like this is the graph that you usually observe whenever you are performing an affinity chromatography. First, you have the equilibration state where the mobile phase is equilibrated through the column. Then you load your sample onto it. where so this curve is basically the proteins or the substances that do not bind to the column, right? So this curve you observe when your proteins do not bind to the column. So this is the work of these particular molecules, the unbound molecules. And then you change it to an elution buffer. You use higher amount of particle by salt concentration or molecules, high amount of molecules that have better affinity for these ligands, and then you change it to an elution buffer. Okay, so before you changing it to an elution buffer, you need to wash it properly such that there are no additional contaminants or other low affinity binding molecules present over here. You wash them, change it to an elution buffer, and you elute it. You will observe a very sharp peak that is of your protein of interest. And you can see that this protein that you obtain after the collection, that is a very much close to a pure protein, because only your protein binds strongly to the ligands, others do not. But in many cases it happens that two or more proteins can have affinity for that. That often happens in an ion exchange chromatography, or even in size exclusion chromatography. Two proteins of similar molecular weights can just elute at the same place, but you do not get a very pure protein over there. That is why affinity chromatography, you know that your protein of interest has a better affinity for that particular ligand. You use that ligand to make your column, and then you load on your protein followed by elution, and you get a pure protein. So this is a more or less the column that we use for the nickel NTA affinity chromatography. Most of you have heard of it, where your protein is histagged, and this histidine binds, the 6-tag histidine binds very well with the nickel ions or even the cobalt ions, and you use it to purify your proteins via the affinity nickel NTA affinity chromatography, right? Okay. So you can see over here there are different types of curves that are given over here. Like in the first one you have the binding buffer, the equilibration state, the flow through, that's the unbound material, and then when you start your elution buffer, you get the eluted target. Similar things happen over here, but you see that the elution profile is very poor because you're not getting a good sharp peak over here. That means either your protein has not bound, or your protein does not show better absorption because maybe it has not bound to the particular column. And you can get multiple types of these types of graphs when you are loading your protein, and you can detect it. So this is not a very good example, neither are these ones, but this is a very fantastic one. From here what you can understand is that in the first case is all of these have an equilibration states, but when you're loading the entire of the protein over here, and then you're starting to elute it. But if you observe in the last one, what happens is that you are loading in different intervals. You are loading and washing, you're loading and washing, you're loading and washing, and then you're eluting. What it does is that it helps the protein to bind properly, not all at a time, but in different intervals, so your protein is not lost. Maybe sometimes it happens over here that during washing, when you're loading the entire protein, the column just gets oversaturated, and your protein just comes out over here, but which you cannot even track. But what happens over here is that you load in different intervals in small amounts, and then you go with the elution, gives you a better profile, elution profile. So all these graphs we call it as the elution profile of a particular protein. Now, like we had for the size exclusion chromatography, we spoke about the beads, the columns. So here we will speak about the matrix. So a proper selection of matrix or carrier of ligands is very important for the stereospecific absorption. Because so the characteristics that these matrices should have is that it should be insoluble, it should have sufficient permeability, highly rigid and suitable particle form, zero adsorption capacity to the other chemicals or molecules. Then it should be chemically stable under the adsorption desorption process, chemical reactivity should allowing the ligands and the specials should be introduced for the proper affinity to your protein of interest. Resistance to microbial or enzymatic attacks, then it would hamper the entire of the column. Your column gets destroyed. Good flow properties for the rapid separation. The mobility should be fine enough. There should not be like if you are using a particular flow rate, it should also be the same inside the column and also in the loops that connect it. And an open pore structure ensures a high capacity binding for even large molecules. So that is about the type of matrix that you're using. It can be of a smaller pore size, but then the different types of columns have different properties. If you want to separate a bigger molecule, you can have a open pore size. If it has a very congested pore size, you cannot actually have binding for the bigger large molecules. So no matrix support is ideal in these respects, where you have the porous glass, cellulose, polyacrylamide, and agarose. Okay. Now the ligand selection. So the selection of the ligand for affinity chromatography is actually affected by the two factors. One is that the ligand must exhibit specific and reversible binding affinity. This is very important. The binding should be highly specific and it should be reversible. Otherwise, elution is difficult. And it should have chemically modified groups to allow it to attach to the matrix without destroying its binding affinity. Like, um, why is it important? Because when you are preparing the column, it should also bind with the matrix. So one end of the ligand should bind with the matrix, and the other end, that is the binding end for the particular ligand to the protein of interest, should be should not be destroyed when we are preparing this column, or the ligand activity should be intact. Okay. And the dissociation constant for the ligand target complex should be in the range of 10 to the power minus 4 to 10 to the power minus 8. Why is it so? Because it falls neither in the category of very low affinity binding or a very high affinity binding. So it is very, means it should be reversible. That is the entire concept. And as well as it should be specific. So the range should be highly, means it should be set up in a way such that it does not bind very tightly or it does not bind very loosely. Okay. The third type of chromatography, where we will be speaking about the charge-charge interaction, which is our ion exchange chromatography. So ion exchange chromatography can be defined as the reversible exchange of ions in the solution, with the ions electrostatically binding to some sort of insoluble matrix or a stationary phase. It is very useful in separation of charged compounds like proteins having differing in one charged by only one charged amino acid, or you can use it to choose whether you want to bind the substance of interest and you want to allow the contaminants to flow away. And this technique is being used widely used for the purification of drinking water, and it is a distinct principle of chromatography performed in a column. So these are not very important points, but what you need to keep in mind is that you want to separate out proteins that has a difference in a particular charge. Only then you can use this particular sort of chromatography for the separation of your proteins. So the basic principle behind this chromatography is entirely relied upon the attraction between the oppositely charged stationary phases, known as the ion exchanger and the analyte. Now the ion exchanger consists of an inert support medium covalently linked to an anion exchanger or a cation exchanger, depending on what type of separation you want to do, what type of charge your protein has and all. Now, to these covalently bound functional groups, the oppositely charged ions are bound, which is the mobile counterion, exchanged with the like charge ions in the sample having charge magnitude more than the ions bound to the matrix. If we have an ion exchange chromatography is performed, negatively charged components will interact. And if we want to have cation exchange chromatography, we need the positively charged components that will be interacting. So the working principle is that if we have a column having the cation exchanger in which the you have the ligand which is negatively charged and your mobile counterion is positively charged. So we have an X plus cation in the sample which has a greater affinity, which has a greater charge than your Y plus. So it binds to your E minus more than that of Y plus. So here also a type of the charge competition just goes on. So now when you want to elute, what you have to do, simple things, competitive charge interaction, you have to use a molecule or a component that has greater charge than that of your protein of interest, that is X plus, and then you elute it. Similar thing is also the same when you want to do a anion exchanger or any sort of ion exchange chromatography. The basic principle is the same. So what are the factors affecting this ion exchange chromatography? So one is the ion exchange resin, that is the swelling factor and the cross-linking, which is important for the effective separation. The cross-linking should be controlled as it affects the exchange's capacity, and the swelling helps in proper exposure of the charged molecules and ions. So the ultimate thing is that the resin should be well prepared for the proper binding of your protein of interest. As simple as that. The nature of the exchanging ions, the valency of the ions matter, the size matters, the polarizability, concentration, and the charge of the ions, right? Also the pH of the mobile phase is very important because it will also, the type of mobile phase, the pH of the mobile phase that you're using can also change the charge of the proteins depending on the pi of the protein, okay, and that can also interfere with your ion exchange. The ionic strengths, actually often what happens if you have low, much higher salt concentration or lower salt concentration, it does not allow the binding, and then the entire thing gets eluted out much before that. uh, it does not undergo even binding, and the entire thing just elutes out in the first step. Then temperature and modifiers, though did not play a very much higher role, but still they are important. The buffer, the pH of the buffer should impart the same charge to the sample ions as present in the column. Like anion exchange chromatography should be carried out with cationic buffers and vice versa, because buffer ion will indulge in the ion exchange, which will be of no use, and then your protein does not bind, and ultimately it just elutes out in the first step, right? So according to the chemical nature, we can classify as different groups from which we try to make the matrices and all. So we have the strongly acidic cation exchangers made, we have the sulfonic acid groups attached to styrene and diphenyl. So these are the matrices, and the divinyl benzene copolymer. We have the weakly acidic cation exchanger, the carboxylic acid groups over here, the strongly basic anion exchangers, the quaternary ammonium groups, and the weakly basic anion exchanger, the polyalkyl amine groups. So these are the different groups which we use when we are preparing the different ion exchangers, right? Now the applications of these ion exchange chromatography is that uh, it has multiple applications in different industries, and when we are trying to purify things, softening of hard water, demineralization of water, okay, measure the additives in food and drug samples, concentrate the metal ions in the sample, separate protein mixtures, that is more important to us, extraction of enzymes from tissue, separation of inorganic ions, amino acids, proteins, sugars, separation, and ion exchange column is also used in HPLC. So these are the few applications that you can just simply keep in mind and study about all of these if you want to know in details on this, right? So that's all from the theory point of view on the three. So the major three types of chromatographies I had discussed: size exclusion, affinity, and ion exchange. Everything has its own advantages as well as disadvantages. So whenever you want to separate out a protein, it's not that there is a manner in which you should carry out the chromatographic techniques such that you get a pure protein. It's not that you just know this chromatography and go about using it, okay? So for example, let me give you one example. Like if you have two 10 kilodalton proteins, okay, in a particular mixture, but your protein of interest is also of a 10 kilodalton size, you definitely go first for an affinity chromatography if there is a tag over there, or go for an ion exchange if you know that your protein has a charge that is different from the other two proteins of the same size. If that is possible, go with that first. But if you simply go for size exclusion chromatography first, it's of just no use. You will, everything elutes at the same place, and then the entire effort goes in vain. So first what you do, go for an ion exchange or an affinity first, separate your protein out from a similar sized protein or the other contaminants, and then go for a size exclusion chromatography, resolve your protein from the bigger sized proteins, and you get a pure protein. So the ultimate goal is to get a pure protein, a pure substance, a pure macromolecule. That is what is important. It never minds in which pattern you go for a chromatography or which type of chromatography you are using. As long as you get your substance or macromolecule in a pure form, that's absolutely fine. Great. Okay. So, right. Just 2 to 3 minutes of break, and then we will start with the question and answers. Okay, so let us start with the questions. You people first try answering, and then probably I can give you the correct one. Okay, let's start with the first one then. Yeah. Okay. See. Yes. So a particular protein can be separated from the contaminating proteins by spectrometry, fractional distillation, chromatographic techniques. Easy one. Okay. The next one. If the partition coefficient is doubled, by what factor changes the molecular weight? So K average. So it is directly proportional to the molecular weight, right? Yes. So when it gets doubled, yes. So if it's doubled, the factor changes by 2 times. Yes, that's right. A. Okay. Which of the following statements is true from the graph for gel filtration chromatography? A and B are more distinctly separated than that of C. B is in dimerized form of A. If the buffer rate is increased, the peaks will get more separated than the original. The molecular weight of C is lower compared to A and B. D. Yeah. So D is the correct one. The molecular weight of C is lower compared to A and B. Void volume in a gel chromatography refers to. So what is the void volume? I was talking about it. Space within the matrix pore, volume of the column, volume of the protein added to the column, or the volume of the column which is unoccupied by the matrix granules. So what is a void volume? No one? Okay. So void volume is the space where your proteins do not usually enter. Yes. So it's the space that is not occupied by the matrix granules. So your proteins do not enter over there. Or even if it enters, it goes into the void volume because there are no beads to where it can bind or where it can enter. Right? In a size exclusion chromatography, Cefadex G200 is used. The column volume is given as 60 ml and the volume of the stationary phase is 45 ml. If the elution of volume of the solute is 40 ml, find out the distribution coefficient. Something interesting now. So you people can answer. In the meantime, I can also show you what's the actual formula and all. If you know, then you can answer me. So V0, or you can call as the void volume, is equal to 1/3 of (20 ml). Right now, what is given over here is the elution volume. So VE is equal to your 40 ml, and you have V as stationary as 45. So now KD to so 20 ml. 20. So yeah, no, A is the correct option. 0.44. Anyways, you can check back this calculation. I guess it's 0.44 if I'm not wrong. Okay, but A is the correct option. Next one. 3 different proteins are to be separated for analysis. The characteristics of the proteins are given below. Which of the following would result in the best separation of these proteins to get them in pure form? So you have the protein A, B, C of molecular weight, different molecular weights and different pI. So which of the following techniques can you use? Paper chromatography, gel filtration, SDS page, ion exchange followed by gel filtration. So SDS page followed by ion exchange followed by gel filtration. You cannot use an ion exchange chromatography because of the similar types of pI, right? So CND goes out. The paper chromatography will not be able to separate or resolve this one. So yes, B is the correct option. Okay. The next one. Carboxymethyl CM matrix and DEAE matrix are generally considered as cation exchange, cation and anion exchange, anion exchange, anion and cation exchange. D. Okay. B, D. So there is a confusion between B and D. So carboxymethyl and diethyl aminoethyl, right? So carboxymethyl means it has a carboxyl group, so it's negatively charged. For separation of, so that matrix is negatively charged. You want to separate out the positively charged ions from that one, and the DEAE matrix is positively charged. You have to separate out the negatively charged amino acids from there. So now which one is the correct one, cation or anion? So CM matrix is CM. CM matrix is what? It's a cation exchanger, and DEAE is an anion exchanger. So B is the correct one. Right. Okay, the next one. Your protein of interest contains a 6x histag and is overexpressed in bacterial culture. After purifying by nickel-NT affinity chromatography, you run the eluted fractions through the SDS page to confirm its presence and purity. However, you observe, in addition to a protein of interest, an additional band. Which of the following explanation for this is true? The histag got cleaved, the protein does not contain a tag, some bacterial protein contains tandem repeats of histidine, or a protein is multimeric. C? Okay. Yeah. So C is the correct one. Your bacterial proteins can have tandem repeats of histidine that also binds to the particular column. So that is the right one, C. Okay. Before loading the impure protein solution in phosphate buffer 7.4 in the nickel NTA column, what will you do? Centrifuge the solution in 11,000 rpm and discard the supernatant. Centrifuge the solution and discard the precipitate. Check the pH using pH meter. Equilibrate the column with mobile phase phosphate buffer 7.4. 1 and 3 are correct, 2, 3, 4 are correct, 1, 3, 4 are correct, 1 and 4 are correct. One, 3 and 4. One is linked 2, 3 and 4. Excuse me. So before loading the impure protein solution, okay, so it's telling that your protein is impure and it's also in its solution. So centrifuge the solution in 11,000 and discard the supernatant is wrong. So 1 is wrong. So 2, 3 and 4 are correct. Okay, because you have to check the pH, though it is not that very important when you are doing nickel NTA chromatography, but in any ways you have to discard the precipitate because that does not contain your protein solution. The supernatant does. because you have an impure protein solution. Okay, so your protein solution contains impurities. When you will centrifuge it, the impurities will come down as a precipitate. So you have to first separate out your protein from the impurities. So the impurities will be in the precipitate. The supernatant contains a more or less of a uh, not a very pure protein solution, but a pure solution. Yes, proteins can definitely settle down. Proteins can definitely settle down, but as long as the question tells that the solution is impure, does not tell that your protein forms an aggregate or it comes into the inclusion body. We cannot tell that it goes into the precipitate. So basically, so that much what I can understand from over here, though it does not clearly tell whether the protein can be in the precipitate, maybe in the supernet, but from what I can understand is that the protein solution is impure. So therefore I can tell that yes, 2, 3 and 4 are correct. One is not correct because the protein, I hope it's soluble. That's a different thing. It's like an inclusion body wash and all. We denature it, and okay. Anyways, I will just. You guys also can check this question once, okay? But how much I can tell is, anyways, whatever you are telling is also very right. So the question does not is not very clear to me. Okay, so you guys can check back if maybe I am wrong over here. Okay, so you can check with this question, and you can, if you get a better answer to it and it's workable, then it's fine. Okay, or I will check back once, and if you ask me in the next class, I can also tell you that if that works for you all. I think that's better. Yeah, now there can be two things. Whatever you are telling is also correct because the protein can be in the supernet, but if your protein is in the impurity, then in ideal scenario they have not provided 1 and 2, means in the options we do not have both 1 and 2 is correct, because what we usually do is that first we do not discard anything, because this discarding thing is very dicey. You never know where your protein will come. So your protein can be in the precipitate, can be in the supernatant, you never know. Okay, so then what we do is that we first load it onto the column. If we see that we are getting a good elution profile, that means the protein was there in the supernatant. Or what we do, we run a gel, we check whether it is in the supernatant or in the pellet, and then we go for the extraction. So 1 and 2, as long as 1 and 2 is not both correct, so either one has to be correct. And in a protein solution, as long as it is telling, therefore the precipitate thing can be discarded. Okay, but whatever the other portion is that you need to discard the supernatant, that can, we cannot discard the supernatant like that. In this case both 1 and 2 can be correct. Okay, so therefore just check with this. I will also find out if I get a better answer to it, and then you can ask me in the next class, right? Okay, which of the following statements is or are true? In membrane-based filtration method, commonly used to remove high molecular weight compounds, for a common anion exchanger chromatography, sodium acetate buffer of pH 4.5 is used. In an affinity chromatography, only one of the proteins binds to the column material on the basis of specificity and high affinity. In gel filtration chromatography, it can separate proteins based on size. Which of the following is or are true? B, D. So we use this filtration method to remove lower molecular weight compounds, particles, small particles like that. So that is why this membrane-based filtration method is used. So the first one is incorrect. We use sodium acetate buffer for cation exchange chromatography. Okay, so we use it for the cation exchange chromatography. And in affinity chromatography, so 3 and 4 are correct. Yes, D is the correct option. 3 and 4 are correct, but we use no, 2 is not correct. Sodium acetate buffer is used for a cation exchange chromatography. Like, now match the following. This looks easy. Affinity chromatography, gel filtration, cation exchange, hydrophobic interactions. Which one? Which is the correct option? Tell me, tell me. See? Okay, let's see. Affinity chromatography, nickel NTA matrix. So 1, 3. Okay, so A or C can be correct. Gel filtration chromatography, let's come back to this later. We have the cation exchange. So cation exchange, yes, CM cellulose matrix. So 3 is 2. Okay, so this one. Hydrophobic interaction, silica gel, and for gel extraction we have the DAE Cephalose matrix. Right. So C is the correct option. Okay. So a sample contains a mixture of proteins from which protein X is to be isolated. So you have to separate out X from the other 3 proteins, which will be an accurate isolation. Ion exchange chromatography only, ion exchange followed by gel filtration, affinity followed by ion exchange, gel filtration only. So if you can understand that there are 2 factors over here. One is the molecular weight, the other one is PI. So the first is that you need to understand whether you want, so 2 types of chromatographies have to be used. If you want to resolve from on the basis of molecular weight, it's a filtration. The other one is ion exchange. Now, which one to use first? If you forget about the options, if you look at just the options, B is the correct answer. But why ion exchange first? Why not filtration? Okay. So first, what do you do? So when you do an ion exchange chromatography, that will separate out your A and X from B and C, right? Anyways, you can also do gel filtration over here, but the number of components or the number of impurities in the mixture would be definitely more. So first what you do ion exchange to separate out A and X from B and C. Then you go for a gel filtration. What it would do, it would separate out the two different molecular weight proteins from the mixture. So B is the correct option. But if there was an option of gel filtration chromatography followed by ion exchange, that would also have been correct. But if only one option has to be correct, then it has to be this, because when you do gel filtration first, it would, what it would do, it would only separate A from that, and there would be a mixture of B, C and X, right? So the number of contaminants are more along with that are present along X. So you need to, in different stages, you have to remove as many number of contaminants as much as possible. The next one, which of the following is not true about high pressure liquid chromatography, HPLC? It requires high pressure for the separation of the samples of the species. There is no need to vaporize the samples. It is performed in columns. It has high sensitivity. We have not talked about HPLC though, but there was a previous year question. Yeah, actually. So it requires a high pressure for separation. That is why it's named as high pressure liquid chromatography. It's definitely performed in columns. There are different types of columns for separation of proteins and small peptides. Like you have the, if you know, you have the C18 columns for peptides. It is highly sensitive. So but there is no need to vaporize the samples is basically not true. So B is the correct option over here. Okay. Now, which of the following will improve the efficiency of the separation process in liquid chromatography? These were the previous year questions, but I don't know if I haven't talked about it. Okay, so liquid chromatography, increase in sample size, increase in column diameter, reduction in sample size, increase in column diameter. Which one? D. Okay. Here you need to focus on two things. One is the sample. So there are two factors. One is the sample size and the column diameter. If let's first focus on the column diameter. If the column diameter is more, you will see that your sample disperses out more, and that would actually widen up your graph. Okay, because the narrower the column is, the narrower the beads are, it will allow less dispersion. Your protein stays in a particular position, it does not randomly go everywhere. So a reduction in column diameter is very important. So the other thing is that the sample size, uh, the lesser the size, the better will be the separation process, because then it occupies a less space in the a particular column, or the space that is provided to it. For a higher molecular weight, you need a greater column diameter, but more the moment you're increasing the column diameter, the sample actually disperses out, and then the illusion or the separation becomes a problem. So reduction in sample size and reduction in column diameter should be maintained. And the last question, Which of the following statement is true in the FPLC system? The flow rate is maintained at 2 to 5 ml per minute. Increasing the flow rate beyond the limit can cause column breakage. Large air pockets can enhance the protein purity. To 80 nanometer, we can monitor UV absorbance, pH and conductivity of the protein. After elution, SDS page must be performed to check the purity. FPLC is fast pressure liquid chromatography. So basically, this type of chromatography is so. Just let me tell you. So this is a fast protein liquid chromatography, right? So it is also a separation technique for separating out proteins from other biomolecules using a liquid chromatography. It is of high performance, and you can use different types of columns intact. You put different types of columns in the attached to the different loops attached to this fast protein chromatography. These are connected to the pumps. You maintain a particular flow rate, and here these columns are also made up of small beads, so it has a similar working principle. The simple thing is that it does not have a very high number of complicated loop structure over here. Rather, it's made up of small beads. So you can perform actually affinity chromatography by connecting the column to this fast protein liquid chromatography and all, and the pump maintains a flow rate. Okay, so the composition of the protein or the buffer that you're using is according to the type of chromatography that you want to use over here. You can also do an ion exchange chromatography or an affinity chromatography. So this is basically a system. More than a chromatographic technique, it's a system that takes up different types of chromatographic columns or the techniques. You attach the column to this particular system and you do that particular chromatography. Okay, and it's connected to the pump, the detectors and the monitor for getting the curves and all. Okay, so it's simple like that. Okay, so the flow rate is maintained at 2 to 5 ml per minute. Increasing the flow rate beyond the limit can cause column breakage. Okay, so that is right. Large air pockets can enhance the protein purity. That does not seem to be very much correct. At 280 we can monitor UV, pH and conductivity. No, that is also not correct. After elution, that it needs to be, yeah. So 1 and 4 are correct. Yes. That's all then from my part. Okay. If you have any questions, you can ask me. I'm not sure on it actually, because maybe the person who would be taking it can only tell it to you, and NPTEL usually updates you, notifies you on the classes. Because the person taking, I do not know the person who is taking it actually, so uh, yeah, if there is a class so there will be a class tomorrow. So if you're getting a mail, so there will be a class tomorrow. Okay, because I do not get those mails. Okay, so I cannot tell whether there will be or the class is postponed or something like that. I cannot tell you. I can only tell that when I will be taking it, right? Yeah. Okay then, thank you all for joining. We will again meet in the next week.